All right, well, welcome back to our second talk of the afternoon session. It's a great pleasure to introduce Emmanuel Kowalski from Zurich, who will speak to us today on les problèmes des rencontres.
Thank you very much. It's really a wonderful pleasure and honor to be here for this conference in honor of Andrew. So I actually met Andrew for the first time more than 24 years ago, although he probably doesn't remember. He was just giving a talk in Princeton where I happened to be there. I was not yet a grad student even. And since then, I think among the mathematicians that I truly admire is definitely one of the top. I won't say the number, but he's really, really close to the top. So for the mathematics, I mean, he does time and time again mathematics that I absolutely love to look at the statements. And then I cannot imagine for myself I would ever being able to try to prove the way he does it, because I think our mathematical capabilities are very different. And also as a human being is someone I really like. And of course, the wonderful Montreal number theory community, which is a great part of, and with Chantal and Dimitris and the others. These are all things which are really truly amazing achievements. So I'm going to give my talk in English. The slides are in French because we are in Montreal, la belle province. As you can see, there's actually an English version of the slides that you still have time to download if you want to not test your French reading ability. So this is going to be a talk which in many ways is like my t-shirt says is why should you make things simple when you can make them complicated? It's about something which I actually don't understand. I mean, it might be something that it would be not really worthwhile spending more than half an hour on, but I think for half an hour talk, it's actually a pretty good topic. Okay, so let's start. Yes, wonderful. Okay. So le problème des rencontres, or the problem of coincidences in English, is a very, very old problem of probability theory. It goes back to the early 18th century. So to give you an idea of old, so this is 1708 to 1750 at the latest. And at that time, Montreal was a French town. It's not the reason I chose it, but it happens to be the case. So the result is one of the very, very first, maybe the very first problem about random permutations. It's of course inspired by games of chance, card games in that case. And it's remarkable because it's very, very simple, and yet the result is not so trivial. It's probably the first appearance of the Poisson distribution in mathematics, well before Poisson. So the mathematical statement is here as a theorem. So of course, that's not the way it was stated in these olden days, but mathematically nowadays, you take a random uniformly chosen permutation on Sn. So I call it X sub n. Then notation, let's write fix of sigma for the fixed points of sigma. And you try to study the distribution of the number of fixed points. So the problème des rencontres, the original one is, what is the chance that there are no fixed points really? And this would be like a bet you would play. So the banker would put 13 cards numbered from 1 to 13 with Jack, Queen, and King as the 11, 12, and 13. And then you would have to bet if you pull successively the same number of cards, one in front of each other, what's the probability that you get the same number at least once? That's the problème des rencontres. And so the people who worked on this in this time, there's a Frenchman named Pierre de Montmort, was pretty good, fairly amateur mathematician, but really pretty good if you read his book. So he wrote a book in 1708. He then got into a correspondence with the first Nicolas Bernoulli, who is not the best known of the Nicolas Bernoullis, but is also pretty good. And then in England around that time, there was Abraham de Moivre, who a little bit later wrote also a book about games of chance, where he redid or recovered and improved some of this analysis. So these books are highly readable. I mean, I actually read some of the things of both of them, and they're actually very, very nice to read. So this is the kind of thing you read in Pierre de Montmort. So you can see there's funny things like the parentheses are not there. So this P times P minus 1 is P times P minus 1, and not P times P minus 1. So you can see both in this and in Abraham de Moivre. So that's taken from de Moivre, which is in English. So when they describe a game of chance, they are struggling to find the right way of presenting the people. So de Montmort is starting to get the right idea. So he called them Pierre and Paul. the moivre is very close to the truth, so he calls them A and B. And presumably, he missed Alice and Bob by just a few years. Okay, so that's the problem. This is the theorem. It's actually very simple to prove it. Let me first restate it explicitly. So what it means to converge in law to the Poisson distribution of parameter 1 is just you look at how many permutations have k fixed points. For k fixed, you take the density in the symmetric group, and the Poisson distribution is 1 over e, 1 over k factorial. So in particular, you can compute 1 over e by this kind of random methods long before Buffon computed pi by throwing needles. Okay, and as far as proving this is the statement is something you can give to anyone who knows what is the number e, essentially, and the proof is not more complicated. So this is a more or less complete proof. Let's count how many permutations in Sn of k fixed points. Well, the set of the k fixed points can be any subset of k elements among n. And once you fix the set of fixed points, well, you need to count permutations of n minus k elements, which have no fixed points at all. So that's the n, the number of derangements, that's a standard terminology. And then the next big idea is to use inclusion-exclusion to count the n. So you start with all permutations, then for each possible fixed point, there are n of them. There will be n minus 1 factorial will get them. If you do this, you get nothing left, but you add up again the two fixed points, n minus 1 over 2 times n minus 1 factorial, and so on. The series is not infinite, of course. At some point, you stop because you don't have enough numbers to permute anymore. But that's inclusion-exclusion. And in particular, in de Moivre, it's done in a very interesting formal way. It's almost like he's struggling to invent some set theory to describe the inclusion-exclusion procedure. It's very interesting. And then once you've done that, then 1 over n factorial is going to give you the probability, the binomial coefficient. So dn, you have a formula here, but now you replace n by n minus k. So it's n minus k factorial, and then 1 minus 1 plus 1 over 2, blah, blah, blah. And you just need to know that exponential of minus 1 is the power series with factorials, and you get the result. So as a theorem, it's really quite simple. I personally like this statement a lot because I think it's one of the most elementary that I know, where you start with a problem of pure probability, but it's probability about discrete algebraic objects. The answer has to do with analysis with 1 over e. And in the proof, you have this very important inclusion-exclusion. And it's also probably one of the first times that inclusion-exclusion was used explicitly to solve a problem in mathematics. Okay, so that's like the classical proof. And now I'm going to explain the proof that we stumbled on recently with Arthur Forey and Javier Fresán. We didn't start trying to prove this theorem in a new way, but we ended up doing that in a strange way, which I hope will be, although there will not be so much number theory until the very, very end. So we start with a simple interpretation. So that's very standard. If you have a permutation, what's the number of fixed points? Well, one way of seeing it is it's a trace of the permutation matrix. There's nothing to say about this. It's very, very simple. Then the second step, the way I presented is we need to a way to test convergence in law. So there's the way I was describing earlier, which you explicitly compute the probability of reaching every element. But there's another way, which is also very frequently used, which we saw this morning also in some other contexts, the method of moments. And the Poisson distribution has moments which are small enough that this is really an if and only if to test for convergence. So if you can show that the case moment for every fixed k of the number of fixed points converges to the corresponding moment for the Poisson distribution, then you are done. You have proved convergence in law to the Poisson distribution. So that's what we're going to do. Then the next step, you need a little bit of algebra or elementary representation theory. So it's very easy to see in this case, and it's a general fact, whenever you have a finite group acting on some linearly on some finite dimensional vector space, the dimension of the space of vectors invariant under a group can be computed by doing the average of the trace of all the elements in your finite group. So in our case, that would say that if you average the number of fixed points, which is what we want to compute, that's the average of the trace of the permutation matrices. That's going to be, therefore, the dimension of the subspace of C to the n on which the permutation matrix act in the usual way, and this subspace must be invariant by all these permutation matrices. Okay, so in fact, this subspace is of dimension 1. It's trivial to compute in that case, but that's just the first moment. Now, if you want to do the case moment, k is a non-negative integer that's fixed. Well, it's the same principle, but you have to replace each permutation matrix by its case tensor power, which concretely means the following. So sigma is a permutation of n letters. So by post-composition, it permutes the maps from 1k to 1n. And you look at the matrix of permutation of size n to the power k, which corresponds to this action. So you have to order these n to the k things if you really want to write the matrix, but that's basically what you need. Okay, and now that's when we start doing something weird. So this moment is actually quite computable. I mean, you could very well write this as the sum of over n over I, such that sigma of I is equal to 1, raised to the power k, exchange the sum, compute, you will get the result that you want at the end. But so the way we found to do this is very weird. And that's why I put this quote from Keats, which I actually got from P.G. Woodhouse. So it's something very strange. There is, for an indeterminate value of t, so variable, there's a very strange mathematical object that has been defined first by Deligne in 2004, and then refined and reinterpreted by Knopp in 2007, which deserves to be called the symmetric group on t letters. Okay? So t is an indeterminate. You can also think of it as a complex number. You can specialize to any complex number. So of course, it's not a group in the usual sense. So that's why I put it in green and in quotes. But it's something that exists. And there is then a notion of permutation matrices of size t coming from this construction. And then you can compute the dimension of the invariant subspace under this action of st on c to the power t, whatever that means. And the thing is, this dimension is dimension in the usual sense. So it's actually a nice fine dimensional vector space, and you can compute the dimension, and that's something that exists. And this construction, which is super abstract, and again, we came to it in a very strange way, it has a property or two properties which are important. So the first is you can specialize t. So t a priori is a variable, but you can specialize it to be a non-negative integer n. And when you do this, there's this correspondence. So the c to the t becomes a c to the n. The matrices of permutation become permutation matrices. And it's possible to check that the dimension of the invariant subspaces can only drop down by specialization. And again, if you look at the formulas, you realize that it's not only true, but there's actually equality when when n is at least k. So k is fixed. It's the moment we want to compute. Let's say 10. We want to compute the 10th moment. Starting from n equals 11, we know that the dimension we want to compute. Okay, so the left-hand side is the case moment of the number of fixed points of a random permutation, a true one. And this right-hand side is this weird thing defined by Deligne and Knopp. Then the second property, which follows from this construction of Deligne and Knopp, is that there is a canonical basis for this invariant subspace. And it's given by the set of partitions, so sets theoretic in non-empty finite subsets of the set of numbers from 1 to k. So these two properties together, even if you don't know anything about the Poisson distribution, they tell you that there is convergence in law, and they tell you what the limit has to be. Okay? Because it tells you that the number of fixed points, the case moment on average, converges to this number, which is often called B sub k, the Bell number of partitions of integers from 1 to k. And its convergence in a very strong sense, it's actually a constant sequence from some point on, which is a fact that was known already at least since Diaconis and Shashan in 1994. Okay, and so to conclude the proof, you just need to know that the Bell number is the expectation of P1 to the power k. So it's the case moment of the Poisson distribution. So that's a fact that's often attributed to Dubinsky. I looked at Dubinsky's paper, and as far as I could see, what Dubinsky did is compute the case moment for k equal 1 to 8, and observe that each of them is a multiple of 1 over e. But he never writes down a formula in terms of this BK number, the partition numbers. Okay, and so I said, it is a fact that's been known for a long time that the moments of the Poisson distribution are these numbers. It's not hard to prove it a priori because they both satisfy the same recurrence relation. It's very elementary to check that the number of partitions satisfies that bk plus 1 is the sum of binomial coefficients, k over g times bj. And this equation for the moments of the Poisson distribution is a special case of the so-called Chern-Stein equation that kind of characterizes the Poisson distribution and which is used for Poisson approximation in probability theory. We have a proof. I mean, it is really a proof, and it's not, despite these green numbers and these green things, it is completely a proof. But you might ask, is it really an honest proof? So first, one question is, after all, this was a very, very simple theorem, and we prove it in a very, very complicated way. And moreover, I didn't tell you what are these constructions of Deligne and Knopp, and it could be that somehow there's so much information on the symmetric group hidden in the construction that I would be proving a theorem by using information that goes way beyond. So I'm going to try and address these things to explain that I'm not saying it's the best proof, but it is the proof which contains some information a priori. So one thing is, because Knopp's construction in particular, it's not just specialized to the symmetric groups. There's some input data, which was the symmetric, with those finite sets that gives rise to these symmetric groups with T elements. But you can use other data, and this, if you just do the same proof, will lead to theorems which are much younger, and in some cases were not known, or at least we didn't find them in the literature. So one case that was known due to Fullman in his PhD was, if you have a finite field, now you replace the random permutations by random elements in GL and E, uniform, and you look at the size of the fixed point set, which is just the size of the kernel of 1 minus yn, that this converges in law, as far as I know, was not proved or not known before Fullman, and it follows exactly in the same way, straightforwardly. Moreover, by again changing the parameter, we can also deal with the fine groups over this finite field. So translation plus a random element in GL and E, and this we didn't find in the literature. I mean, I'm sure it can be done with methods of Fullman and Stanton, but we didn't find it. Okay, and this is characterized, so the limit is characterized by the case moment being the number of subspaces, linear or affine subspaces in e to the power k. So e to the power k being a k-dimensional vector space. So the parallel with the permutations is kind of intriguing. You might have expected some different answer, because here we have subspaces instead of partitions, but that's what we get. So I should say this, actually, I said you need to just do the same proof, but there's a small epsilon in addition, which is due to the fact that the number of partitions is small. So the moments of the Poisson distribution are small, which means that the method of moment works for the Poisson distribution. Now, if you try to compute the number of subspaces in e to the power k, so most of them will come from dimension about k over 2. And they are parameterized by an algebraic variety of dimension n times k minus n. So you get something of dimension about k squared over 4. And the number of points on algebraic variety of dimension d over a finite field is q to the power d, where q is the size of the finite field. So you have a case moment which is of size q to the k squared over 4, more or less. Now, if you know the method of moments in probability theory, that's typically where people have to tell you that, okay, you have to be careful, the log normal distribution, so the law of the exponential of a standard normal distribution, has moments exponential k squared over 2, and is not uniquely characterized by its moments, which means that to prove this, you actually have to first check something about the probability of this distribution that ensures the method of moment is applicable. Now, and this is, well, there's a little bit of number theory, because actually distributions kind of similar to that do show up in Cohen-Lenstra heuristics, in heuristics on Selmer groups, on theorems on Selmer groups, and in particular, the little epsilon we need here in that particular case is found in the paper of East Brown on the distribution of Selmer groups for the congruent number problem. We need one slight extra information. One needs to know that the support of possible limits have to be powers of the size of the finite field. That helps to get the result, at least in the way East Brown proves it. Okay, so that's kind of new theorems we can prove with this method, and no computations are involved. And it is nice to have the same argument in unifying these different cases. And there are some very weird other cases we can probably get from Knopf's construction that we don't understand at all yet, including some where you have solvable P groups and things like that, which, okay, I don't really know what they mean. Now, the other thing I like in this proof myself is, I mean, it's a problem with this convergence in law in general, at least to me, is that it's such a strange form of convergence. You know, the limiting distribution can live on a completely different probability space. All the things that you take the limit can live on different probability space. So when you get a certain limit, let's say the Poisson limit, like in this case, where does this limit come from? I mean, is it just a coincidence? Is it just some numerical fact that you're checking? In the first proof, it looks like that. So here we have an interpretation of the limit. This Poisson limit is not an arbitrary thing, at least intuitively, and I'm sure that this has useful applications, is you take a uniform permutation of T elements, where T is a variable, you take the image by the trace of the permutation matrices, whatever they are, that gives you a distribution on the real line, and this turns out to be this Poisson distribution. Okay? Now, the thing is that taking a subgroup of matrices of some fixed size, taking the trace, taking the image measure of the R measure on this is what most people call a SatoTate measure, like we saw this morning in Ken's talk. And so we have here somehow an interpretation of the Poisson distribution as some kind of SatoTate measure. And by using a slightly different construction, you can also recover the standard Gaussian in a similar way as some kind of SatoTate measure, which is a limit which had been observed by a number of people, both in random matrices and in number theory. So Mike Larson had observed that you can get such things a long time ago. Still some open questions. I mean, I said we don't pretend to understand what we're doing. I mean, it might be just some nice but innocuous observation that's not going to lead to anything. It could be that this is some nice way to predict or recover certain asymptotic facts in the theory of random permutations, because it seems that this ST, whatever it is, contains information which is non-trivial about asymptotics of random permutations. Like there is a tensor product on this thing, and you can recover the so-called stable Kronecker coefficients in this way without taking any limit. But for instance, you might want to do the same computations of fixed point for symplectic groups over finite fields. This is what Fullman also did. With his methods, it's not particularly different. You have to adapt the linear algebra. And we don't know how to do that because there's no construction either by Deligne or by Knopf or by anybody else, which for the moment kind of interpolates these symplectic groups. It's very surprising, but that's a fact. Now, the second thing is actually very, very annoying to me. So if you've ever studied the number of number of fixed points in a random permutation, you probably want to compute the number of 2 cycles, the number of 3 cycles, and then the joint distribution, fixed points, 2 cycles, 3 cycles. And it's not so much more difficult to prove using the methods of counting or Diaconis-Shashani that the whole sequence, fixed points, 2 cycles, 3 cycles, and so on, converges in law to a sequence of independent Poisson distributions with parameters 1, 1/2, 1/3, 1/4, and so on. It's not so hard. Now, at the moment, we cannot prove that. I mean, it's pretty certain that we can prove that there is some distribution, there's some convergence in law for the 2 cycles, for instance. It's a problem in the theory of symmetric functions. There's no question we should be able to do it. I have no understanding of why it should be Poisson. From the way we would have to do it, I see absolutely no way to see for the moment that it will be Poisson. And in terms of independence, it's even worse. There has to be something that we're missing, but I don't see it for the moment. So that's something I certainly hope to be able to answer. I have to learn symmetric function theory first. Okay. And now I'm going to finish with something which is a bit more arithmetic, and it's highly speculative, but I find it very amusing to think that if it works, it would be something very, very, very nice, as you will see. Okay, so let me start by recalling a theorem, which everybody who does elementary algebraic number theory has seen. So one way is that random permutations are linked to number theory is by studying what happens when you take a polynomial with integral coefficients, let's say, and then you look at its Galois group, like in the previous talk, and you look at the number of roots of this polynomial mod p when p varies. And it's a theorem that was only conjectured by Frobenius, and then it's a consequence of the Chebotarev density theorem, that if you look at the statistics of the number of roots mod p of a fixed polynomial g, then as you average over the primes up to x and x goes to infinity, this has a limiting distribution, which is the number of fixed points of the Galois group, viewed as a permutation group of the roots. So if you take a random polynomial, as we saw earlier, the Galois group will be Sn. And so this means that if you look at the number of the roots of a random polynomial, and then you look at large primes on average, and you look at the distribution of the number of zeros, you will find this number of fixed points of a random permutation in Sn. And the reason is due to the fact that the permutations of the roots are reproduced by the Frobenius operation. So sending x to the p, it permutes the roots. That gives you a permutation up to conjugacy, which turns out to be equidistributed in the Galois group, and generically, therefore, in Sn by Chebotarev. So one may ask, can you find a way to have this weird pseudo-symmetric group St appear in a similar arithmetic situation? So I don't know, but here is a way that might work, possibly. So it's something that we looked at with sound in our recent paper on the Chinese remainder theorem. So we looked a little bit at these weird functions called pseudo polynomials in the sense of whole. And the simplest of them is the floor function for e times n factorial. So it's 1 plus n times n minus 1 and so on and so on. At some point you have to stop. I guess I didn't write it correctly. I should have write 1 plus 2 plus 2. Okay, anyway. So the fraction, the floor of e times n factorial. So this has the property that if you look at it modulo q, it's always q periodic, which means that you can define a reduction modulo q as a function from z mod qz to z mod qz for every q. And then you can look at how many roots this has. You can ask yourself, well, what's the distribution of the number of roots when you let, again, p goes to infinity and take the average over larger and larger ranges of primes. So here is a conjecture that we make. So I checked with sound that it's okay to call this a conjecture. So we conjecture that this converges to the Poisson distribution with parameter 1. And therefore, to the size of the fixed point set of a random permutation, this ST6. And here are the numerics. Like Lior, I think that number theory, it's nice to be able to do numerics. So these are the moments of primes less than 10 to the 6 for this number of zeros. So this function satisfies a simple recurrence relation, which makes it easy to actually compute the number of roots mod p, not by computing e times n factorial for n of that size. So the first moment should be 1, second moment should be 2, third moment should be 5, fourth moment should be 15, and the numerics are pretty good. One has to be a bit careful. It's a fact that you cannot always expect that if you take a random pseudo polynomial, which is not a true polynomial, there will be something like this, like Vivian Kuperberg constructed examples of pseudo polynomials which have no roots except frankly many, I think. So for which you wouldn't have a Poisson distribution. But for this one, the numerics seem pretty good. I personally would be very, very happy if there was an actual link with these weird permutations. And in any case, I think this is quite a nice conjecture. I mean, I hope that someday someone will make progress on that, although it sounds pretty hard. Okay, thank you very much.
Thanks very much, Emmanuel. Are there any questions or comments?
Andrew has one.
Ah,
The strange F is periodic mod Q.
Yeah, it's periodic mod P for every prime P. Yeah, that's what it means to be a pseudo polynomial. It's kind of the simplest one in some sense.
You made a surprising comment that Bell numbers are small, which is not what.
Well, I mean,
combinatorial.
for the method of moments, they are small.
So they came up as an expectation of a moment, right?
Yeah.
Or the
Right.
dimension of the space. And of course, they have a nice generating function, e
Yes.
to the x minus 1.
Right.
So I'm wondering where these other situations you're working in, and you've got the full set of moments as the number of subspaces. Do they satisfy some recurrence like the Bell numbers?
Yeah. So, and in the paper of, well, not so much in Fullman because it's unpublished, so I don't know. But in Fullman and Stanton, they make this analogy. They try to write generating series. They have analogs of Stirling numbers, and they have all kinds of formulas which are kind of Q analogs, where Q is the size of the finite field of the Bell numbers. Yeah. There's some. Yeah. It's just these moments are pretty big. But like, I mean, I talked to Will Selwyn recently about something independent, and I mean, in his recent paper with Melanie Wood, where they study also various distributions on various kinds of groups, you also get situations where typically the moments are way too large for the method of moments, but they are starting to get an understanding of kind of like a super generalization of East-Brown's lemma, which would presumably mean that now at the moment, whenever I want to change the situation, I have to check that East-Brown's lemma generalizes, but there should be some like very algebraic thing that says that any kind of these limits, distributions on subspaces that you could get from Cohen-Lenstra type heuristics should all satisfy some uniqueness in the method of moments, which is by itself is actually a very, very nice fact. I mean, it's surprising in some sense.
Do you have an upper bound on the number of zeros of your function f?
For the number of zeros of this function f, we know nothing, I think.
So it could be p for all we know.
It could be that there are no zeros from some point on. I mean, for this one, I think that there's a related one where there are two obvious zeros. But for this one, if I remember correctly, we know nothing. It could be that there are no zeros for p large enough.
any other questions for Emmanuel?
Oh, so the question is, yeah. The question is, if you take these y-ends to not be uniform, but something else. So I don't know if this has been studied at all. I mean, certainly the kind of this weird algebraic method I'm describing has no chance to work with anything that's not uniform, as far as I can see. And in his paper, it's all based on more or less explicit computations of probabilities with linear algebra over finite fields. So I think it's also pretty dependent on using uniform measures, but maybe there are some deformations, natural deformations that would also work. But I didn't see that mentioned in that paper.
Any further questions? If not, let's thank Emmanuel again.